Hey everybody, in this video, we are going to go over 2 FRQ questions based on the topic of states of matter. Now, the first question comes from the 2018 AP Chemistry exam, and it states, the table above gives the molecular structures and boiling points for the compounds CS2 and COS. So let's look at this and see what it gives us. It gives us the molecular structure and the boiling point. And that's pretty nice, honestly. So let's look at A. In terms of the types and relative strengths of all the intermolecular forces in each compound, explain why the boiling point of CS2 is higher than that of COS. So let's draw out CS2. CS2 looks like this, and let's draw the lone pairs. And COS looks like this according to the diagram. And let me draw the S over there. So it states that it wants all the intermolecular forces for each compound, and we need to use that to explain why it has a higher boiling point. So in this diagram, we can draw 2 bond dipoles, and we see that they cancel out since they're the same. And because of that, this has no net dipole, so CS2 will have only LDF. Now what about SCO? Well, this arrow will be longer than this arrow since oxygen is more electronegative, and you will get a net dipole going to the right side, and therefore you will have dipole-dipole and London dispersion forces. Now it says, explain why the boiling point of CS2 is higher than that of COS. Well, at first I expected that this would have the higher boiling point since it has dipole-dipole while LDF lacks it. So why does this compound end up having a higher boiling point than this compound? This must mean that this compound has stronger intermolecular forces than this compound, even though this compound has 2 intermolecular forces. So we have to think about this. Perhaps the LDF force on the CS2 compound is higher than the combination of the dipole-dipole forces and the LDF forces on the SCO compound combined. So this means that the LDF on the CS2 compound is greater in terms of strength overall than both the LDF plus the dipole-dipole forces for the COS compound. So this is the only explanation for why CS2 has a higher boiling point. And yeah, that's what A is. Now let's look at B. B is going to involve some math, and let's look at it. A 10-gram sample of CS2 is put into an evacuated 5.0 liter rigid container. The container is sealed and heated to 325 Kelvin, at which temperature all of the CS2 liquid has evaporated. What is the pressure of the container once all the CS2 has evaporated? Well, I think we have to use PV equals nRT. And CS2 has a molar mass of, well, I don't know. Let's see what the molar mass is. 12.01 plus 2 times, let's see, 32.07. 32.07. And I get that the molar mass of CS2 is going to be 76.15 grams per mole. And we simply have to convert 10 grams into moles. So 10.0 divided by 76.15 will give us 0.131 moles of CS2. So it says that they put this in 5.0 liter container, and they then said that they heated it to 325 Kelvin, where all of the CS2 turned into gas. So there are 0.131 moles of gas. Now it says, what's the pressure? So PV equals nRT. Let's do it. P times V 5.0 is equal to N, which is 0.131, times R 0.0821, times T 325. Doing the math, 0.131 times 0.0821 times 325 divided by 5.0 is going to give us a pressure of 0.70 atmospheres. So let's not put the S because it's just ATM. And let's check the answer and see if we got it right. So the first question has this for its explanation. CS2 has only LDF, while COS has LDF and dipole-dipole forces. Now, when you write your answers, remember to write the full name. Don't write LDF, because not everybody knows what LDF is. Instead, you have to write London dispersion forces in your answers whenever you're doing free response questions in order to be as specific as possible. So, we read that. So, the London dispersion forces in CS2 are stronger than the combination of London dispersion forces and the dipole-dipole forces in COS. So that's basically what I said about how the LDF was greater than both the dipole-dipole and the LDF of the COS molecule. Now let's look at B. So for B, we did everything right. We got an answer of 0.70 atmospheres. And from what I understand, I think that you have to put your units for your answer, of course, and you probably have to put the units for the moles of CS2, just like what we did, but I don't think you have to necessarily put the units when you're doing the math. And I don't know if this is 100% accurate, so go check with your teacher if you're going to take the AP Chem exam to see if you need to include units when you're showing your work. And personally, I don't do it. I just put the units at the end and for any important numbers. So yeah, that's what I do. And look at the point scoring. They only give you points for the number of moles of CS2, and they give you points for the correct answer with the correct unit. So it doesn't seem like they're giving you points for putting the right units in your work. So, I don't know if you have to put liter ATM over mole times Kelvin. I mean, that could be just for the sake of accuracy, but personally I don't do it because it takes forever. So let's actually go back because I just showed you the answers, and let's look at part 2 or number 2. So we start with C because I skipped over some information that's not related to this chapter, and C says S2Cl2 is a product of the reaction. In the box below, complete the Lewis dot diagram for the S2Cl2 molecule by drawing in all of the electron pairs. So, we have to complete the Lewis structure. So, we know that sulfur needs 2 bonds, chlorine needs 1 bond, so let's get to it. So, if we just connect all of them with one line, we see that all of them have what they need. Each chlorine has 1 bond and each sulfur has 2 bonds. Now we just have to put the electron pairs. So, 1, 2, 3, 1, 2, 1, 2, 1, 2, 3. Alright, let's look at C2. What is the approximate value of the CSS bond angle in the S2Cl2 molecule that you drew in part CI? If the two CLSS bond angles are not equal, include both angles. So, let's look at this diagram. So they want the CLSS bond angle. So we have to think about this, and let me redraw this. So I think this is going to be bent because, I have that feeling, and I'll tell you why I have that feeling. So this kind of looks like hydrogen peroxide, and you see that this has a steric number of 4, and there are 2 bonds and 2 lone pairs. And if you remember from the diagram for Vesper, you know that this is going to be bent, and you know that this has a steric number of 4 with 2 bonds and 2 lone pairs, so this is going to be bent as well. And if you remember, if there are 2 lone pairs and 2 bonds, I usually call it 105 degrees to mimic that of water. So I think the answer to this could be 105 degrees. Now let's look at D. CCl4 can also be produced by reacting CHCl3 with Cl2 gas at 400 degrees Celsius as represented by the reaction below, or equation below. And that's the equation. They're all in a 1-to-1 ratio. At the completion of the reaction, a chemist successfully separates the CCl4 gas from the HCl gas by cooling the mixture to 70 degrees Celsius, at which temperature the CCl4 condenses while the HCl gas remains in the gaseous state. So the first question says, identify all the IMFs present in HCl liquid. So let's draw out HCl, and let's draw the lone pairs, and we know that there's going to be a bond dipole, so this is going to be polar, and thus in HCl there are going to be dipole, and I'm going to spell this out all the way because in free response questions we want to be as specific as possible. So dipole, I know that says pipole, but it's dipole, forces, and London dispersion forces. And yeah, those are the two forces present in HCl. Now let's look at double I. What can be inferred about the relative strengths of the intermolecular forces in CCl4 liquid and HCl liquid? So let's think about this for a second. They want to justify the answer in terms of the information above. So the information above tells us that when they have, of course, CCl4 gas and HCl gas, they say that at I don't know, what is the temperature? At 400 degrees Celsius, they're both gases. But it says that when they cool down to 70 degrees Celsius, the CCl4 condenses first, and the HCl is still a gas. Now this tells us a few things. It tells us that the boiling point of CCl4 is higher than that of HCl, because if we draw a nice little diagram over here, we can label this at 70 degrees Celsius and this at 400 degrees Celsius. We can figure out where the boiling points are. So it states that when it cools down from 400 to 70 degrees Celsius, it says that the CCl4 becomes a liquid from a gas. So this means that the boiling point, or the condensation point, at the point at which it became a liquid from a gas, is somewhere between. So let's just say this is the boiling or condensation point of CCl4. Now we decrease the temperature, but the HCl is still a gas. That means that we haven't hit the boiling point yet. So this must mean that the boiling point must be further down the line over here. So this means that CCl4 has a higher boiling point than HCl. Now because CCl4 condenses first and has a higher boiling point, this tells us that the intermolecular forces in CCl4 is greater than that of the intermolecular forces in HCl, since the CCl4 condensed first, which means that the forces between CCl4 molecules must be stronger. So that's how I used the information above to get my answer. And now let's read the explanations that College Board gives. So College Board drew the Lewis dot diagram, and that's cool. It looks the same as what we drew. And they let us have a bond angle of between 104 and 1110. We wrote 105, so we are A-okay. Now, what about D? So the answers here are as follows. So there's dipole-dipole forces and London dispersion forces in HCl, so we got that. Now let's read the explanation they give for II. So the intermolecular forces among CCl4 molecules must be stronger than those among HCl molecules because the CCl4 condenses at a higher temperature than HCl. Or in other words, CCl4 has a higher boiling or condensation point than HCl. And we got that from the information above because we know that CCl4 condenses first. And yeah, that's all for this video. Have a wonderful day.